Welcome to Vectors 1. It will be the first of 3 slideshows, hopefully, that I narrate on the vectors algebra unit. This one's pretty straightforward. It just covers finding resultant vectors, but it's definitely on that online test, so I want to make sure you know how to do it. Okay, so let's talk about what a vector is. Directed line segment. So when I talk about a scalar, I'm talking about quantities like distance or speed. They have a magnitude. So if we look on this chart here, the distance is 32 meters. Okay, that's scalar. The minute I add a direction, the minute I say northwest to the east, at 18 degrees, I've added a direction and I've taken my scalar quantity and turned it into a vector. When you do draw vectors, they get a name. Usually I try to remember to do that. I don't always. If there's an arrow above it, it means a vector. If I'm talking we're in a vector unit, it's probably a vector. So just bear with me because I am lazy. The other important one we have to know for this first slideshow, when you use R, it means a resultant. So this is like the sum vector after we do all our vector addition. Okay, so vector addition. If we take a bunch of vectors and add them together, we can get a resultant, and we can get a quantitative one, and we can do it qualitatively too. So what are vectors here? So I've drawn a Cartesian plane, and I'm kind of just going to make this one north, east, south, and west. Never eat shredded wheat if you're always trying to remember. So let's say my house is right at the origin. Ooh, okay, there we go. So I'm going to leave my house and I'm going to walk 2 kilometers north. So I'm making a vector because I'm going a distance, which is 2 kilometers. I'm going north and I'm stopping here. Okay. And then I'm going to walk 4.5 kilometers southwest. So this one's going to be, bear with me, a little bit of a guess. And a little bit of bad drawing. So let's pretend that's 4.5 kilometers southwest. And then I'm going to walk 3 kilometers east. And I'm going to end up here. So qualitatively, I know that I am about this far away from my house. But when we use vector addition, we can find that number quantitatively, which is awesome. Okay, so qualitative again. So how do you add vectors? What did I do in that last thing? I went one direction for a bit, then I went another direction, and then I went a third direction. Okay, so I created 3 vectors. And my resultant vector always connects, no matter how many vectors you have, your origin with your last stop. So this is your resultant here. Okay, and when you look on this thing, if you take A and you add B, your resultant vector is A plus B. But what if I had done B, sorry, terrible interpretation of B, and then added A? My resultant vector, and this is awful because it doesn't look anything like it, but had I been a better illustrator, it would have been identical. So this is the one we just did, starting right here, 2 kilometers north, 4.5 kilometers southwest, and notice that, in ideally this would be 2 units, this would be 4.5 units, but I'm sketching so it's not. And then 3 kilometers east, and apparently our pen just quit. And we get a resultant vector here, and it goes from the origin to the end. I don't know what's going on there. Okay, let's try and recover over here. In this one, we are looking at standard position. So let's revisit some trig. Remember 0, 90, 180, 270. Okay. So if we have a vector that is 10 meters per second at 170, it's kind of going to be, let's say 10 is this long. I'm arbitrarily deciding that. So we have a vector that looks like this. That's me recreating it off the Cartesian plane. And then if we have a vector that's 5 meters per second at 300, let's say it's half of that. That is awful. And let's recreate it over here like that. So what happens? I go A, then I go B. Sorry, terrible. And my resultant vector is right here. And once again, if I had done A first, or B first rather, oh, good Lord, then A, I should have produced the same resultant vector, although I didn't because I can't draw. Okay, so how are we going to do this with a little more math? We're going to use rectangular components of vectors. Now, there are a lot of ways to solve vectors. Right now, we're just going to look at the rectangular components. Okay, so that means you're going to take your Pythagorean theorem. You're going to find the x side of any triangle. You're going to find the y side, right, the opposite and the adjacent. And if you do that for each of your vectors, resolve it into its x and y parts, you can combine all those x and y parts and find the x and y parts of the answer. So here we have a vector, A. I'll give him a little hat. Oh, this will probably go. There we go. Excellent. Okay, and we're in standard position, so we've got a little theta here. So you'll notice that if I just translate that AY over here, we're back to little trig setup, where we can easily say that if I wanted to find AY, I would be looking at the sine thing. So I would say, oh, AY sine theta, right, equals AY over A, because that's y over r, and that's what the sine relationship is. So if I really wanted to isolate AY, so as long as we're working in standard position, the vertical component of any vector is going to be the magnitude of the vector multiplied by the angle from the horizontal. And you'll be given these. So you don't have to do all the trig. If you're looking for the x component of a vector, here it is, the magnitude times cos of the angle, and the y component, the magnitude times the sine of the angle. And just remember, that angle must always, always, always be in standard position. So let's try an example. So we have a vector A, and it's 15 newtons, pardon me, and it's at 134 degrees. Okay, so if I want to know what AX is, magnitude of the vector A, 15, times the cosine of the angle in standard position. I cannot stress that enough. AY, magnitude of the vector, times the sine of the standard position angle. Okay, and if you do that math, you're going to get negative 10.42 newtons for the x, and you're going to get 10.79 newtons for the y. This is good. Leave this alone. Do not take away the negative, because it means that the x component is moving to the left for this vector, and we want to leave the signs alone because if we use this method where we always stay in standard position, everything will work out perfectly, so don't touch the negative. Okay, so let's look at number 2. So what's the magnitude and direction of a vector that runs from 1, 3 to 2, negative 3? Not on the origin, that's fine. There's 1, 3. I'm going to tap over here. And we're going to do 2, negative 3. I'm going to try and draw a circle so it doesn't tap. Is right there. And 1, 3 disappeared. So we'll do that. So we're looking at this vector here. Okay. It's not on the origin. I mean, we can move it if we want to, but we can work where we are, because it's really kind of like this, right? Where we have the AX and the AY. And we have our reference angle theta, and we have a right angle here. We went from 1 to 2 in the x direction, so this side is 1 log. We went from 3 to negative 3 in the y direction, so this side is 6 log. And off you go. Okay, so if I want to find the magnitude, I'm finding the full vector, so I'm going to get r equals, there's only one, I'm calling it r, the root of x squared plus y squared This is Pythagorean theorems, root 37. Great. So now we have a magnitude, but we also need a direction. So let's look at this triangle we made it. And we always want to reference the horizontal direction. So we've got this theta, which will be a reference angle, because we're not in the first quadrant. Or, you know, if we were thinking about the direction, it's not going to end up in the first quadrant. And we're going to take y over x, right? Because that's what the tangent is. Okay. So if we want to turn that into math that we can actually do in our calculator, we're going to use that arctan, the inverse tan, and make sure you put things in the right place. The y goes on top and the x goes on the bottom. And when you do that math, you're going to get 80.5 degrees. So is the angle 80.5 degrees? No. Okay, so when we look at this picture, or even this picture, if we draw our line and pretend our Cartesian plane is actually here, from 0, we're going around here. So to do the math to find the actual angle, we're going to do 360 subtract 80.5 degrees. So the angle, the real angle, is going to be 279.5. So final answer, root 37, pardon me, at 279.5 degrees. Magnitude and direction. Okay, so those were places where we had one vector. But if we have multiple vectors, infinite number of vectors, it's the same thing. You're going to take the vectors and you're going to put them all with the tail at the origin. So you're just going to make them a bunch of things in any sort of direction. And you're going to resolve each one into its x and y parts. You can add all the x parts together, ax plus bx plus cx, keeping the signs that they have, and you will get rx. You can add all the y components together, ay plus by plus cy, and then you'll get the ry. And then you can use Pythagorean theorem to find the magnitude of the resultant, and you can use your tan button to find the direction. Okay, so now we're going to take that original question where we walked 2 kilometers, then 4.5, then 3. Notice this time all the vectors have been put with their tails on the origin. So A is our 2 kilometers north, so the x component is going to be the magnitude of the vector, which is 2 times the cosine of the angle north from standard position is 90. 2 sine 90. Okay, and then for B, we're going to take the magnitude, and we're going to do cosine of southwest, which is 180 plus another 45, 225 degrees. And I always use the standard position because it makes me have to do no work with sines. It'll make all the signs perfect. Okay, and likewise for C, we have 3 cos, and we're going east. East is 0 degrees. And we have 3 times sine of 0 degrees. Okay, so when I do the math, I get 0. When I do the math, I get negative 3.2. Fine. When I do the math, I get 3. When I do the math on my calculator, I get 2. When I do the math, I get negative 3.2 again. And finally, when I get the math done, I have 0. So basically, to find the resultant x, I'm going to add 0 plus, let me just do it, 0 plus negative 3.2, just keeping the signs very, very clear, plus 3, and I'm going to have a resultant x of negative 0.2. Same here, 2 plus negative 3.2, which is the same as 2 minus 3.2, plus 0 gives me negative 1.2. Okay, so I have the x and y components of my resultant vector. I'm just going to write those down here. I knew I'd run out of room. Okay, same thing, Pythagorean theorem. R squared equals root x squared plus y squared. So I mean, whether you leave the negative on or off doesn't matter. It's going to disappear. Let's make sure we get that all the way across. And you're going to end up doing that math. And in this case, because I'm doing distance, since I'm not going to leave it as an exact answer, I'm going to change it to an actual distance and decimal. Okay, 1.22 kilometers. Likewise, we're going to get the reference angle. And make sure you check out the formula sheet for this unit, because there is one that is specific to it. Alright, we're going to put the negative 1.2 over the negative 0.2, and you can use absolute values here because this is a reference angle, so we're kind of going to mess around with it anyway. And you should get, oh, another 80.5. There you go. Just by fluke, not by design. But think about where this one is. Look at your signs on Rx and Ry. X is negative, so you get negative X here and here. And you also need negative y. So the place where you get both x and y negative is in the third quadrant. So if you want to find an angle in the third quadrant, you have to go 180 and you have to add your reference angle, your 80.5. Ah, no. Okay, so your angle is right here. So we're going to take 180. We're going to add 80.5. And we get 260.5 degrees. So final answer, you are 1.22 kilometers away from your house at a bearing of 260.5 degrees. So what would you call that? South, south, west, or something like that. But just leave it in standard position. That's fine. Okay, so now I'm just going to go through a couple more practice examples, so this really is ingrained in your head. Same thing. Take A, resolve it into x and y. The math for this is going to be 10, the magnitude, times the cosine, always cosine. These angles are in standard position already, so I'm good to go. Okay, and if I do that math, I'm going to get negative 9.8. That's fine, leave the sign. That's a point. And over here, I'm going to get 1.7. Bx. It's 5 meters per second. It's velocity at 300 degrees. By. 5 meters per second. Sine 300 degrees. Okay, and here we go, and that should give me 2.5. Oops, and this one should give me negative 4.3. So Rx, I'm just going to draw a little line there so it's like I'm doing math, negative 9.8 plus 2.5, negative 7.3. Ry, the y component of the resultant, 1.7 minus 4.3, negative 2.6. What quadrant is this thing going to be in? Right here again, negative x, negative y. Okay, so same math. I'm going to take the square of the x component, add it to the square of the y component, and then take the root of our answer. Do all that math, and hopefully you'll get 7.75 meters per second, which is now looking like 775. That's a 7.75. I'm afraid of my click on this thing. Okay, and I'm going to go over here. My reference angle is going to be 2.6, and notice I'm dropping the negatives because I don't want to deal with thinking about it, divided by 3, and that is a tangent, so in order to get it I'm going to do the tan to the negative 1 of that, and I'm going to get 20 degrees-ish. I think it's 19.6, I'll round it up. And because I'm in that third quadrant, I know that my actual bearing angle, standard position angle, will be 180 plus an additional 20. equals 200 degrees. So if you're uncertain about that, make sure you ask me about how to do the reference angles again, because it's been a while since trig, but especially if you're going to rewrite the trig. You want to know that. Okay. I don't even know what happened there. Okay, let's go back. There we go. Whoop, to that 180 plus the 20. Okay, final answer, 7.75 meters per second at 200 degrees. Okay. Sometimes you'll get these questions where there's a lot of vectors. And, I'm going to call this one A because it's the thing I did first. I'm going to call this one B. And call this one C. Now, just looking at this picture, I don't know where that one ends because I clipped it off by accident. I know that my resultant is going to be something like this, taking the original start position, going to the last tip. But I would like to solve this mathematically. Now, we have to be careful because we've got angles here, but they're not the right angles. So if I look at vector A, yeah, it's 54 kilometers, but it's not at 18.7 degrees, and this is so important. You must change everything to standard position. It's actually at, what on earth? It's actually at 108.7 degrees. Okay, and what is that? 90 plus 18.7. Okay, that will get me to the actual number I need. So I'm going to try and erase this. Whee, that worked. Okay. B. The value is right, 64.5, but it is not at 15.6. In fact, if you look at B, it should be at starting here and going all the way around like that. So B is actually at 360 degrees subtract 15.6. So it's going to be at 344.4 degrees. And C, the magnitude is the same, 72.4. They're giving us 31.8. And in this case, I don't usually like you to mess around with the 270s and 90s, but this is for counting purposes. 270 plus another 38.1. So 270 plus 38.1 should give you 308.1 degrees. All right, so here we go, setting up. Okay, AX 54 multiplied by cosine 108.7. I'm just trying to go quickly through it. AY 54 multiplied by sine 108.7. BX 64.5 multiplied by cos 344.4. BY 64.5 multiplied by sine 344.4. CX 72.4 multiplied by cos 308.1. CY 72.4 multiplied by sine 308.1. Okay, we should add these together, keeping the signs, and you are going to get 89.5 for your RX. Let's circle that. And you're going to get negative 23.2 for your RY. Now I'm going to carry this over to the next slide. Writing it down again, RX 89.5, RY negative 3.2. Okay, resultant vector, the usual, root of 89.5 squared plus negative 23.2 squared. I'm going to keep it as a decimal because these are actual distances, and you should get 92.5 kilometers. Our reference angle is going to be the arctan of RY over RX. Make sure the Y goes on top. This time it looks like I kept the sign. and it gave me negative 14.5 degrees, whatever, 14.5 degrees, same deal. So that's our reference angle, but that's not the angle we're at. We always have to check. So let's look at what we've got. We've got positive x and we've got negative y. Positive x can be here or here. Negative y can be here or here. So quadrant 4 is the only place they can both be. So we're going to be in this quadrant, which means in order to find the angle, the real angle, we're going to take 360 and subtract 14.5, which gives us 345.5 degrees. Okay, so that's our answer, 92.5 kilometers at 345.5 degrees. And if you go back, yeah, that could be something like that. It's long, it's longer than the other ones. It's at that kind of angle. Sorry, my guy is not working here. So that's vectors 1, and I will get vectors 2 up post haste.